Hello everyone and welcome to our semiconductor webinar. In this webinar we have the pleasure to show you an overview of wafer inspection and also tell you why machine vision plays a key role in it. And also during this webinar you have the chance to ask questions because we're doing a Q&A session later. So simply write your questions in the chat. And before we start, I also would like to introduce ourselves. And since I do not like to talk about myself, I would start to introduce you, if that's okay, Coco.
Yeah, that's okay.
Wonderful. So you're my colleague. She's Coco Rogers. She's working for customer services as an application engineer for, I think, almost 3 years.
Yes, that's correct.
Perfect.
And this is Marco Setzer. He's our marketing specialist and working at NVTech since 6 years. That's quite a long time.
It is. And also, Coco, since I already introduced you, you are taking now the role of being the technical expert in this webinar. And I try to give this whole session a structure because I collected some questions from visiting customers, from talking to people on the trade shows, and straight from the industry. So with these questions, I try to structure the webinar. And if everything is set, I think we can start, right?
Yes, we can start.
Perfect. Cool. So the first question is actually from my side. Can you give us a quick overview? What do you think we cover in this session? What do you think the audience will know after this webinar?
Yes, of course. So the first thing is how machine vision can be used to detect defects on a wafer. And we even brought a live demo to demonstrate that. Second thing is which technologies from NVTech Halton can be used to maximize the yield. And the third point that we're going to cover is how we can support you to start with your automated optical inspection.
Sounds good. And to underline how important that topic is, I got a little question for you.
Okay.
So if you think about all the wafers which were produced in 2024, and if you would lay them end to end next to each other, what do you think how big the area would be in terms of football pitches, since we are in Germany and we like football? So maybe you can have a guess how many football pitches.
Okay, that's a tough question. Maybe 500?
It's even more. It's 1,100 football pitches.
Oh, okay.
And 7.85 million square meters. So it's really a lot, and I think it highlights quite good why this is a focus industry for machine vision. And with this, I would like to start and to begin with you, who can probably guide us through the front-end process and tell us why the continuous optical inspection is so important.
Yes, of course. So a semiconductor wafer is built up layer by layer, and if in every process, it requires a precise sequence of processes. So with every layer, it requires a precise sequence of processes, including material deposition, resist coating, lithography, etching, and ion implantation, after the resist is again removed. And at every step, you need a thorough inspection of the wafer to ensure that there are no defects or anomalies which could impact the chip performance.
All right. So now let's turn our attention to our little setup here you brought. So can you tell us briefly what this demonstration is showing?
So this demo exemplifies the inspection of a finished wafer IC structure before dicing, as in an AOI routine.
So AOI means?
Automated optical inspection.
All right.
Exactly. And it is capable of detecting even the smallest defects, like, for example, dust particles.
Cool. So a question regarding this demonstration we always encounter on trade shows, for example, is about the hardware. People are always asking on which hardware is the demo running. Can you tell us a little bit about that?
Yes, of course. So we can see here a 12-inch wafer lying on a plate that is mounted to an XY table. And this XY table makes it possible to move the wafer below the camera to ensure a thorough inspection. Up here we have a lucid camera for high-resolution images, and down here a low-angle ring light to enhance the defect contrast.
So you already talked about the resolution, and with this specific hardware now, which resolution can be reached, you would say, and also can you tell us a little bit about the defect sizes maybe?
Yes, of course. So the camera here has a resolution of 12 megapixels, and we have an inspection area of about 5 by 5 millimeters, and the whole field of view is about 10 by 10 millimeters. 1 pixel in the image corresponds then to 2.7 micrometers in the real world. So we can detect defects of about 8 to 10 micrometers, but in general, it always depends on your defect size. So the smaller your defect, the higher the resolution has to be.
All right. So, but you could also use other hardware like line scan sensors or contact image sensors, I guess.
Yes, that's also possible with MVTech Halcon, and for the inspection of the complete wafer, it is common and also recommended to use a line scan setup. So now, Markus, we saw the hardware setup, and I think we can now run the system live and take a look at the acquired images.
I'm ready. Let's go.
Perfect. So first, the wafer has to, the XY table has to move into the starting position, and the chips on the wafer are organized in a grid structure and can be inspected iteratively by moving the wafer below the camera. And in the visualization, you can see on the left side the acquired images of the chip, and on the right side you can see the wafer map showing the current location on the wafer.
So let's break it down for a second. Let's summarize for a second. Now we have high quality images which are showing the chips we want to inspect.
Yes.
And I could see some tiny little scratches. What other defects could occur?
So the surface has to be inspected for issues such as etching residuals, particle contamination, scratches, and also impurities from handling. So different defects that can occur throughout the production process. And the step of defect detection has to be repeated after every new layer is applied, so multiple times throughout the inspection production process.
Okay, so what we often hear from the industry is that it can be really problematic and also expensive if defects are not discovered early on in the wafer production process, right?
Yes, exactly. So if they're not detected, these defects can compromise the yield and also the reliability of the chip. So without early detection, we maybe only find it in the final testing step, and then you have already put a significant amount of resources and time into that chip. And by catching the defects early on in the production process, the manufacturers can reduce the waste, can improve the yield, and enhance the overall efficiency of their production process. And not to forget, save money.
I like saving money. What I also like is technology. So let's dive a little bit deeper into the technology.
Yes, of course.
So the question which might be asked from the audience and also from my side is, what technology did you use?
So for this optical inspection, we use MVTech Halcon's robust and fast shape-based matching algorithm and also the variation model. The optical inspection consists of 2 steps. So in the first step, we train the shape-based matching model to robustly locate the chip in the image, even if the position of the chip varies throughout different images. And in the second step, we train the variation model to detect different defects and also really small defects in the image.
Okay, I think with that, if you like, you could guide us a little bit through the single steps of the vision algorithm.
Yes, of course.
Cool.
So I prepared a script, and in the first step, we see just the image that we acquired, which you also saw in the live demo before. And now we have to define a matching region. The matching region doesn't have to be the whole chip. It just needs as enough descriptive structures. So it's also enough to just take the inner part of the chip, as you can see here. And with that and some training images, we can then train the matching model. Here also the extended parameter estimation is used to estimate a few parameters so you don't have to set them manually, which makes it a lot easier. Now in green, you can see the extracted contours that then can be used for the alignment of the chip, because we need that to generate the training samples for our variation model. So we're now gonna run the matching and crop the images and align them. And these images can then be used to train the variation model. For the variation model, we define a golden sample, also called ideal image, which you can see on the left side. This is an ideal chip without any defects. Then we also have a deviation image, which you can see in the middle, called a variation image. And on the right, the standard deviation image. If we now have an image of our chip we want to inspect, we're going to compare it to the golden sample and the variation image to detect the defects. So Markus, now we trained a matching model and we also have the variation model. I think we're ready to run it live on the demo. What do you think?
Sounds great. For our technical directors, this is the moment to switch the camera directly to the setup, because I think we're all curious about the final result.
Okay, perfect. So I'm going to quickly explain what you can see now. So on the left side, you can see the result of the matching and the variation model. So the chip is located, it is aligned and cropped, and the defects are found and are marked in red. On the right side, you have again the wafer map showing you the current location on the wafer, and the colors in green and red tell you whether the chip was classified as okay or not okay. So you can see also on the top and left that the matching takes about 4 to 5 milliseconds, and the variation model is even below 1 millisecond, which is super fast. Halcon can, of course, also be used for further processing. For example, now we have detected the defects. We maybe would also like to classify them into different defect categories. And then we could, for example, draw conclusions about the cause of the defect.
So if you look closely here, you can see that most of the chips which are inspected are considered as NOK, so not okay. Can you tell us why is that?
Yes, this is because we have a lot of dust particles on the wafer here, and that's because normally wafers are produced in a clean room and not in the office. So this demo should just exemplify how such a inspection process could look like, and that is possible to detect even very small defects using optical inspection.
Okay, perfect. So key takeaway is wafers are not produced in the office.
Yes.
What is also very important is the matter of time, because time is money, so it is very important also for the industry to be fast. How long does it take to set up an optical inspection like this, for example?
Yeah, that's a good question, Markus. And I have to give an answer that nobody really wants to hear. It always depends. So on your specific setup, also on your requirements, for example, regarding the processing time, on the images you have, like how good is the resolution, what kind of defects do you want to detect. So I can't really give a general answer here, unfortunately, but to estimate it more precisely, we can help you, and also we do offer free evaluations. So this can also give a bit more clarity, and there are also colleagues in the US, China, Taiwan, and across Europe that can support you locally if needed.
Okay, thank you very much. I would like to come back to the technology. I think an interesting observation is that if you look back in a couple of years, maybe 2 or 3 years ago, people were really surprised if we showed a demonstration with AI. They said, oh, cool, this is running on AI. Nowadays, it completely switched. If we show a demonstration without AI, people are surprised. And I think it's also interesting because this demonstration is also not running on AI.
Yes, you're correct. So these are classical approaches, and we try to always find the approach that fits the application best. And in this case, classical methods just made more sense in terms especially of hardware requirements and processing time. And yeah, we do not use technologies just because they're popular, but because they work best in practice. And of course, Halcon supports deep learning since 2017. And for further processing steps, like for example, the classification that I mentioned, you could use deep learning, of course.
So as a conclusion, you can say design follows function in this case.
Yes, exactly.
That sounds good. Because I know the question will anyway occur later, maybe you can tell me already. Can I find this code somewhere?
Yes, you can. In Halcon 2505, there is a standard example, and that exactly covers this demo and use case.
Cool.
So Marcus, you asked me a lot of questions. I think now it's my time to ask you a question. What are your key takeaways from today's webinar?
Okay, you turn the tables now. For me, I think the three most important things are: first, defect detection through optical inspection is very important in the early stages of wafer production, since it maximizes the yield and also the reliability. Secondly, I would say that the combination of shape-based matching with a variation model is a very fast and robust approach to detect even tiny defects on a wafer. And third, I think we all agree, because you demonstrated so well, we now have an overview about the whole process of setting up such an optical inspection. So I think these three key takeaways are the things I will remember for sure.
Okay, perfect. and my job is done.
No, not yet, because I got even more questions for you. I would like to be the quiz master again. So I think since we are almost reaching the end of our webinar, it's now time for the Q&A session.
Yes.
And I started to collect some questions during your presentation. And I will refresh one more time our page and see how many questions we got here. So let me quickly. All right. Okay, we got a lot of questions. Also a lot of complex questions I can see. Maybe we start with one compliment. Because somebody's
That's always good.
Yeah, somebody's writing, the algorithm is very fast. Thank you. Can you tell us what hardware is this demo running on? Yeah.
Okay. Yeah. So this demo is running on a standard laptop CPU, and because it's classic approaches, this is sufficient. But if you now would decide to also integrate deep learning, you would need a powerful GPU for that.
So it varies if you need deep learning or not?
Yes,
hardware.
Exactly.
Okay, okay, interesting. So a second question, let me check which one is suitable. This is also interesting, I think. It's about the variation model. The question is, how is the variation model actually trained?
Okay, that's a quite complex question, but I give you a rough overview. So the variation model, to train that, you need a few images that are all aligned. And then there are two methods, robust and standard. And they just differ in how they compute the golden sample that we saw before. The one takes the mean of all the images for every pixel, and the other one takes the median. And yeah, if you want to have even more information, just take a look at that documentation. And we have also multiple standard examples.
Cool. Thank you, Coco. I think we can cover one more question if you like.
Okay.
Wonderful.
I'm ready.
So there's one more question about, starting to implement all of this. Somebody's writing, how can I make sure that your software, so MVTech software, can solve my task? This is also quite interesting, I guess.
Yeah, so I can understand that you want to make sure that the software solves your task before you buy it, and that's why MVTech offers free evaluations. So if you have already images of your production process, you can just send them to us, and we can make an initial evaluation to show you that it works. And if you're still struggling with the hardware setup, we have a large network of certified integration partners that we can get you in contact with.
Sounds good. So I think free evaluation is very important here, and also support in many different languages.
Exactly.
Cool. All right, Coco, we got even more questions, but from what I see, these questions are kind of complex. So it is probably a little bit too much for this webinar. But this is the good thing. If you got more questions, and also the question here, we will answer afterwards anyway. So if you get more questions and want to ask it, just get in touch with us, and I promise all these questions which are here will be also answered, but we get in touch with you individually, a difficult word for a German, to make sure your questions are answered. So I think with this, Coco, we can wrap up the webinar. What do you think?
Yeah, that sounds good. Also, we often do showcase this demo and a lot of other demos at multiple trade fairs, so maybe we see us there.
That sounds great. Check out our websites to see on which trade shows we are. And also, if you've got any questions or feedback or whatsoever, make sure to contact us, and we are happy to help. So thank you very much for your attention at home. Thank you very much, Coco, also for your nice explanations.
Yeah,
it was a pleasure and a lot of fun. So I hope to see you all next time and have a good day. Bye-bye.